Something else to remember. Section 2.6 is limits involving infinity and asymptotes of graphs. So here's a graph of a function y equals 1 over x. When we went over the formal definition of a limit, we said that x had to be approaching some real number c, only now we're letting x approach infinity or negative infinity. And what we have here essentially is a horizontal asymptote. I'm assuming you've all had college algebra and you know what asymptotes are. And when you look at this graph right here, you can see that as x goes off to infinity, what is the function approaching? 0, so that's a real number limit. So there's our limit, 0, as x goes off to infinity. And as x goes off to negative infinity, we're still approaching 0. So this is the formal delta epsilon definition for these limits at infinity. We're not going to go over it. We're not even going to discuss it. Okay, we're moving on. So, in this problem, the instructions say to find the limit of the function as x approaches infinity and negative infinity. Okay? So we're looking at the limit as x approaches infinity of 2 over x minus 8. Okay? Well, one of the things you need to know is the limit of a constant is a constant. That's not going to be a problem. As x goes off to infinity, though, let me give you some background information here. The limit as x approaches infinity of 1 over x is equal to 0, and the limit as x approaches negative infinity of 1 over x is equal to 0. We can tell that, and you've already told me that, just by looking at this graph up above, correct? So it's obvious, it seems obvious that if you divide by infinity or negative infinity, you're going to get 0. That's not a very precise mathematical way to state things, but it's effective, it works. 1 divided by, if you keep using bigger and bigger numbers that you're dividing into, you end up with smaller and smaller values of the fraction. Well, 1 over x, as x goes off to infinity, you're going to get 0. So the limit of this is going to be equal to, using our properties of limits, 2 times the limit as x approaches infinity of 1 over x. All I did was I took that 2 in the numerator and I brought it out front, minus 8, because the limit of a constant is that constant, right? So that's going to be equal to 2 times, what's this limit? 0 minus 8, and that is negative 8. So there's the limit as x approaches infinity. Guess what it's going to be when x approaches negative infinity? The same thing. All right. Right here, we use the fact that the limit of a constant is that constant. Any questions? All right, all the limit laws in Theorem 1 are true when we replace the limit as x approaches c by the limit as x approaches infinity or negative infinity. That is, the variable x may approach a finite number or positive and negative infinity. There's our theorem. We're just going to believe that it's true. If you want to see a proof of that, look in the book. Next, we're asked to find the limit of a function as x approaches infinity and as x approaches negative infinity. So what we have right here is going to be, let's see, part A, we have the limit as x approaches infinity of 9 over 13 plus 1 over x. By direct substitution, what is this going to be when we plug in infinity? That's going to be 0, so we end up with what for our final value of the limit? Part B is the same thing. We look at the limit as x approaches, not infinity now, but negative infinity. All right, as x goes to negative infinity, the limit of 1 over x is equal to 0. So this ends up being 9/13 as well. What that means is this graph would end up having a horizontal asymptote at 9/13. Okay? Any questions? Oop.
So you're just assuming that 1 over x equals 1 because
the 1 over x, the limit, yeah, the limit, and will you have the graph? We're going back to this graph. This is a graph of y equals 1 over x. As x goes off to infinity or negative infinity, the value of the function goes to 0. Always. We've proved it once graphically, or we've shown it or observed it graphically, so we can then use that fact from now until forever. Okay? All right, this one's not the same. We don't get off so light with this one. All right, find the following limit. Now, prior to me teaching you this, I would expect you to look at that and say, no way, don't know how. There's no common factors. If we use direct substitution, we end up with infinity over infinity, and that's an indeterminate form. So then you say, oh, well, I can factor something. Not really. So that doesn't help us either. So here's your out. When you see something like this, and it works only if you're looking at the limit as x goes off to either infinity or negative infinity. What you want to do to manipulate this argument is divide every term by the highest power of x in the denominator. Now you say, well, that's not valid. Why am I doing that to every term? Well, it is algebraically valid because remember, with a fraction you can multiply it by 1 and not change anything, right? So what I'm going to multiply this by is the highest power of x here is x squared. Watch this. I'm not worried about that 7th power right now. What I'm going to show you is that 1 minus x to the 4th over x squared plus 5x. I can take this and I can multiply or distribute the highest power of x is x squared. So I'm going to multiply the top by 1 over x squared, and I'm going to multiply the bottom by 1 over x squared. And isn't that the same thing as multiplying this fraction by 1? Because I have 1 over x squared on top, I have 1 over x squared on bottom. If you have the same value on top as you have on bottom, this is multiplying by 1. Well, now I need to distribute this to both terms here and here. So what that's going to give us then is 1 over x squared minus x squared divided by 1 minus 5 over x is equal to, yeah, I think that's right, is equal to, this is the same thing as saying 1 over x quantity squared minus x squared over 1 minus 5 over x. So this would be equivalent to looking at the limit as x approaches negative infinity of 1 over x squared minus x squared over 1 minus 5 over x. By direct substitution, Oops. That's raised to what power? The 7th. By direct substitution here, and because 1 over x as x goes off to negative infinity, that limit is going to be 0, right? So that gives us 0 minus infinity, because I square a negative infinity, I get a positive infinity, but I'm subtracting it, over 1 minus 0. And this is all raised to the 7th power. Well, 0 minus infinity is, and negative infinity over 1 is negative infinity. So this is equal to negative infinity. Now, we used to say that means the limit doesn't exist, right? We're going to go, because the limit has to be equal to a finite number. I'm actually going to let you say this limit is equal to negative infinity. As x goes to negative infinity, this function goes to negative infinity. Okay? Yes?
So what you're trying to do is manipulate it so that you get a 1 over x.
So that you get a 1 in a constant in the denominator, so it, or you're trying to manipulate it so that you're able to either get an infinity or a 0 or a number or something. And here's how you decide how to do that. If you divide every term by the highest power of x from the denominator, you'll be fine. Okay?
How did 5 over x turn into 0?
That's 5 times 1 over x. And the limit as x goes to negative infinity of 1 over x is 0.
You can see it now.
I can see it now.
And so we substituted negative infinity into x squared, and that's how you get negative
Yeah.
infinity.
Well, we substituted a negative infinity into the x squared, and when you square a negative, it becomes positive, but there's a negative in front. So it stayed negative. Good deal. Okay, we're looking once again at the limit as x goes to negative infinity. If we use direct substitution, we end up with infinity over negative infinity, because negative infinity plus 1 is still negative infinity. We can't say that that's negative 1. We don't know right off the top of our head what this is, because that's an indeterminate form, infinity over infinity, plus or minus infinity over plus or minus infinity. So what we need to do is we once again need to go back to the steps here that say divide every term by the highest power of x in the denominator. Well, what's the highest power of x in the denominator? So we're going to divide everything by x. But over here we have a square root. So we're going to let x be equal to the square root of x squared if x is positive. Right? If x is positive, this is true. The square root of x squared is x. And we're going to let x be equal to the opposite of the square root of x squared if x is negative. Because if you square a negative, you get a positive. The square root of a positive number is a positive number, but x is negative, and a negative number can only be equal to a negative number, so we have to stick that negative in front there. Here, x is going to negative infinity. So underneath this radical then, I've got to, or not under the radical, whenever I multiply the numerator by x, I'm going to write my x with the square root so that I can look at this, but that square root's got to have a negative out in front of it. Okay? So let's look at the problem. We have the square root of x squared plus 1 divided by x plus 1. And we said we're going to divide by the highest power of x in the denominator. Well, that's x to the first. So the denominator I multiply by 1 over x. The numerator I multiply by negative 1 over the square root of x squared. Now, do you agree that the value of the numerator and the value of the denominator are the same when x goes to negative infinity?
Why are you using the negative on this?
Why am I using the negative right here?
Yes.
Because in the problem right here, x is going to be a negative number. So because x is a negative number and I multiply by a negative number in the denominator, I'm also going to multiply by a negative number in the numerator. But when you square a negative, it's positive. The square root of a positive is positive, so I'm saying this has to be negative. Okay? So now here comes those fuzzy, pesky rules of radicals and fractions and negatives all wrapped up in one. And we're going to be careful to make sure we get this right. First of all, a positive divided by a negative, or negative times a positive, is negative. And then we have underneath the radical, this becomes x squared over x squared plus 1 over x squared. Because I distribute, since both of these terms are under the radical, I can move that x squared into the radical and distribute. Do you remember that rule? If you have the square root of a plus b divided by the square root of c, that's going to be the square root of a over c plus b over c. Now you okay? Yeah, I got to remind you of those rules. I don't mind. So this is all over x plus 1 over x when I distribute. All I did to go from here to here is I distributed what was in red over here. So now that gives us negative square root of 1 plus 1 over x squared divided by 1 plus 1 over x, right? So we can now look at the limit as x approaches negative infinity of negative square root of 1 plus 1 over x squared divided by 1 plus 1 over x. By direct substitution, when we plug in a negative infinity right here, what is that whole term going to? 0. So that gives us negative 1 on top, right? And this term is going to, so that gives us a 1 in the denominator. So this whole thing is equal to, had you have not put the negative in there, you would have gotten the wrong answer. And this is because we're going off to negative infinity. If we were going off to positive infinity, we would have gotten a positive 1. Yes, sir?
On that step in the red right there, so you're saying that numerator is the same as the denominator?
In value, yes it is. Because remember, and the only reason it's the same right here is because x is going to a negative number. So this is negative, right? When you square a negative, you get a positive. And when you take the square root of a positive number, you get a positive number. So I had to insert that negative. That's what this bolded red part is. It explains why the negative has to be there.
So it's just manipulating more.
It's just making things line up. If x is negative, it's guaranteeing equality. Yes, sir?
Is that a step that we're going to have to memorize?
No, not memorize, just remember. And it only comes into play if x is going towards a negative infinity. And about the third or fourth test, you're going to get L'Hopital's rule, and you don't have to worry about this anymore. It gets really nice. But in the meantime, we make you suffer for a little while. Just a little longer. And then it'll get fun. All right. So a line y equals b is a horizontal asymptote of the graph of a function, either if the limit as x goes to infinity of the function is b, or the limit as x goes to negative infinity of the function is b. That's why I told you at the very, very beginning when I started this lecture, we're dealing with horizontal asymptotes. Okay? Now, because of that, if you remember your algebra, you know you don't even have to deal with calculus to do your horizontal asymptotes, right? You could just look at the power of the numerator over the power of the denominator. You know, if you had me for college algebra, then we'd go over this. All right? So let's do one more with calculus, and then I'll summarize the rules from algebra so that you can just look at these and know what the answer is going to be. Okay? So we're going to find the limit of this as x goes to infinity and negative infinity, parts A and B. I'm just going to do A, okay? So we're going to look at the limit as x goes to infinity of 6x to the fourth over 18x to the fourth plus 8x cubed plus 2x squared. This is going to be equivalent to the limit as x goes to infinity. In our head, can we go ahead and divide every term by x to the fourth? You know we're going to do that, so that's going to be 6 over 18 plus 8 over x plus 2 over x squared. Is everybody okay? What I did was I divided every single term, like we said we were supposed to do, by the highest power of x in the denominator. The highest power of x in the denominator is 4, so I divide everything by x to the fourth. Well, when I divide 6x to the fourth by x to the fourth, I get 6. When I divide 18x to the fourth by x to the fourth, I get 18. When I divide 8x cubed by x to the fourth, I have one more in the denominator than in the numerator, so it's 8 over x. And then when I divide this term by x to the fourth, I end up with an x squared in the denominator. We okay with that? Now, using direct substitution, as x goes off to infinity, these two terms are going to go to what? So this is then going to be equal to 6 over 18, which reduces to 1/3. Any questions? That brings us
You're
to...
multiplying by 1 over x to the fourth. Each side by...
Yes. I'm multiplying the numerator and the denominator by 1 over x to the fourth. Multiplying by 1 over x to the fourth is the same thing as dividing by x to the fourth. Let me say that again. Multiplying by 1 over x to the fourth is the same as dividing by x to the fourth. Because if I have 6x to the fourth times 1 over x to the fourth, isn't that 6x to the fourth over x? Yeah. So it works the same. Right.
How did you cancel out the 8 over x plus 2 over x?
As x goes off to infinity, this term is going to 0 and this term is going to 0. Remember, if we have an x in the denominator, the limit as x goes to infinity of 1 over x is 0. So this part, these terms go to 0. The limit as x goes to plus or minus infinity of 1 over x is 0. Okay. All right, now I'm going to summarize the rules from algebra for you. These are the rules that apply to horizontal asymptotes. You can either go through the algebra and the calculus approach, or you can just look at the problem and remember these rules. I don't care, whatever makes you happy. Number 1. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is at y equals 0. For example, f of x equals 3x plus 2 over x squared plus 4 has a horizontal asymptote at 0. Here the degree of the numerator is less than the degree of the denominator. Oh, less. That could be x to the 5th. And it's still, what, you want me to change that so that it works? So that you can remember that? Let's make that x to the 4th. Okay, that way you don't have to think it's just got to be one less. Number 2. If the degree of the numerator equals the degree of the denominator, then we have a horizontal asymptote at the line y equals leading coefficient of numerator over leading coefficient of denominator. So for example, look at the problem above. Y equals, let's do this, 7x to the 3rd plus 2x squared minus 4 over 5x to the 3rd plus 1 has a horizontal asymptote at y equals what? 7/5. I agree.
Can we say leading coefficient? The first number?
The number in front of the highest power of x. That's what leading coefficient means. Yep, and those are those lost in translation. That's why learning math is almost like learning another language. You've got to learn what all jargon means. And yes, it's the leading coefficient is just the number in front of the highest power of x. Even if I rearrange the order of these terms, I could have put the constant term first. 7 would still be the leading coefficient. Yeah. It's not the first number you see, it's the number in front of the highest power of x. Let me give you another example, because that could get confusing, and I've been known to do this too. Y equals 2 plus 3x over 4x plus 1. This has a horizontal asymptote at what? 3/4. Okay. Pretty good. And then I'm missing an inequality here. Number 3. If the degree of the numerator is less than the degree of the denominator, greater than, then, there's an E and then. You have no horizontal asymptote. If the degree is just 1 more than, you're going to have a linear oblique asymptote. And I'm not going over how to find those in college algebra, and in pre-cal I do, but there's no horizontal asymptote. Yes?
In 2A, for degrees, why is that? Why do they have different degrees?
They don't have different degrees. These are the same degrees. Yeah, that's x to the 1st. This is x to the 1st. Because there's no power. I just didn't put a power there. So the degree is 1, but the leading coefficient is 3 here, and the leading coefficient is 4 here.
Okay.
Good question. Okay. Moving right along then. Let's find the limit of x squared minus 16 as x and here's the graph to make it easier. Let's find the limit as x approaches 4 from the right, 4 from the left, -4 from the right, and -4 from the left. Okay? looking at this first one, as x approaches 4 from the right-hand side, I'll do red for right. So as x approaches, here's 4. As x approaches 4 from the right, this is going off to, as x approaches 4 from the left, this is going off to, as x approaches -4 from the right. Here's the -4, and as we approach -4 from the right-hand side, this is going off to, and as x approaches -4 from the left, positive infinity. Any questions? Make sense? It's fairly straightforward. Definition: a line x equals a is a vertical asymptote of the graph of the function if either the limit as a approaches a function from the right or the left is going to be a positive or negative infinity. That's what we just saw. Okay? Makes sense. So let's look then at graphing simple rational functions. The first thing you want to do is identify any asymptotes, horizontal or vertical. So for 66, do we have any horizontal or vertical asymptotes? We have a horizontal asymptote at y equals 0. Degree of numerator is less than degree of the denominator. We have a vertical asymptote at x equals 3. Right? So the first thing I'm going to do is I'm going to plot my asymptotes. I have a horizontal asymptote at x equals 0, at y equals 0. I have a vertical asymptote at x equals 3. So this is going to help me kind of give me some guidance here. Do I have any intercepts? If x is equal to 0, what's y equal to? If x is 0, y is positive 1. So there's a y-intercept that our graph is going to go through, right? We have a y-intercept. I don't want that to be, draw my graph in red. We have a y-intercept at 0, 1. Okay. So as x approaches 3 from the left, do we have positive or negative values? As x approaches 3 from the left, that's looking at like 2.99, right? I'm sorry, negative 2.99. And that's a negative over a negative is positive. So as x approaches this vertical asymptote from the left-hand side, it's going to be going off to positive infinity. We have our horizontal asymptote here. And then on the other side, then, we know that we're going to be going down towards negative infinity as we approach this asymptote from the right. And there's the graph. Just using a little bit of algebra mixed in with a little bit of understanding of one-sided limits. Okay? And the reason we know that this is going down towards negative infinity is as we approach 3 from the right. When I'm coming in from the right, I have numbers bigger than 3 that I'm subtracting 3 from. That's a positive value. On the top, I have a negative value, and a negative divided by a positive is negative. So I knew I was going down to negative infinity here. All right, let's go to 68. Do we have a horizontal asymptote? Yes. At y equals what? Do we have a vertical asymptote? Negative 1. Do we have an x or y intercept? Both. It's the origin. We have an intercept at the origin. So right here we know we're going to have a point. Our asymptotes are going to be at y equals 2. There's y equals 2. And at x equals negative 1. Okay? So, as we approach this asymptote from the right-hand side, is this going to go off to positive infinity or negative infinity? Negative infinity, because this number is going to be negative, this number is going to be positive, so that's going off to negative infinity, which means that the graph is going to look like this. All right, as we approach from the right-hand side, let's say negative 1 point something, that's going to be a negative value, that's going to be a negative value, and negative over negative is positive. So this one's going off to positive infinity. We already know as x goes off to infinity and negative infinity, we're going to approach the line y equals 2. So we've drawn the graph, going through our reasoning of limits. Any questions? Yes, sir.
Just like a really quick question. So the horizontal asymptote is the numerator and the vertical is the denominator?
No.
Just don't do that.
No, don't do that. The horizontal asymptote depends on the degree of the numerator as compared to the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, our horizontal asymptote is going to be at 0. Those are those three things that I just wrote down. Here, the degree of the numerator is the same as the degree of the denominator. You're looking for a pattern that wasn't there. This is what I'm doing. The degree is the same, so we have a horizontal asymptote at y equals 2 over 1, because the leading coefficient down here was 1.
What about the vertical?
The vertical asymptotes do occur where the denominator is 0. Yes. Okay. Yes? For 68? Once I plotted the asymptotes and I figured out my intercept, I start with the asymptotes always. Then plot any point that you know. And now I know that this point here is going to go off towards this asymptote because it's a horizontal asymptote. That's what they do. But I needed to know, did this go up? Because they can't cross asymptotes close to 0. But I needed to check and see, does it go up or down? So what I did was, as I approached negative 1 from the left, I'm looking at like negative 9, negative 0.9, negative 0.99, and so forth and so on. So if I plug in a negative here in place of x, I know I'm going to get a negative. And if I plug in a negative 0.9 here, I get a positive value because I'm adding 1. And a negative over a positive is negative, so I'm going to negative infinity. Does that help? Do the same thing on the other side only.
How do you find the points? How do you know it's point?
That's the intercept?
Yeah.
All I'm doing is I'm plugging in a 0 in place of x and looking for y.
Okay.
Okay. Okay. Number 70. I guess I should have written down the instructions, huh? Oh, I know what the instructions said. They said sketch a graph with these, find a graph with these given conditions. Not find, draw, sketch. Okay, first of all, f of 0 has to be 0. What does that tell me? F of 0 that means that I have a point 0, 0 on the graph. Right? So I can put a point right here at 0, 0. Right? I'm also told that the limit as x goes either to infinity or negative infinity is 0. This is my horizontal asymptote. So this part tells me the x-axis is a horizontal asymptote. X-axis is a horizontal asymptote because that's where y is equal to 0, right? So I'm going to go ahead and sketch in the fact that this is a horizontal asymptote. Okay? All right. This part, the limit as x approaches 0 from the right is 2. The limit as x approaches 0 from the right is 2. that means that the function has to be, it can't be equal to 2 at 0, but it's going to be approaching right there, right? And the limit as x approaches 0 from the left is -2. So I got an open circle there. How do I know that? Because this is a function. Because they're using function notation. Functions have to pass a vertical line test, don't they? And I've already got 1 point here when x is equal to 0. I can't have more. So I know these are going to be open circles because I already have a closed circle here at the origin. Now, I've got to sketch the graph. The only thing I haven't used is the fact that these are going to be asymptotes. So I can make this graph do whatever I want around here as long as it's a function and it eventually becomes asymptotic here. I can make this do whatever I want as long as eventually it becomes asymptotic. Right? I had more choices. I could have done this. Right? I have more choices. I mean, I can do anything I want as long as the endpoints become asymptotic to the y-axis. Because I've satisfied each one of those conditions. There's a lot of leeway here. There's a lot of different correct answers. Okay? And that wraps up section 2.6. This is the last section that's going to be on your exam on